My plan for today is three things. Okay, so first is I want to finish the calculation that I started yesterday about how far apart are particles, depending on whether they're bosons or fermions. Then second, I want to try out kind of a visual way of presenting that distribution of positions that's maybe complementary to the algebraic way. And then third, I want to talk about the final exam and plans for that. Okay, so to begin with, right, let me remind you, we were in the midst of doing this big calculation yesterday. And so here I have the same whiteboard notes that we were working on before. Okay, so to back up to where we are, okay, I'll remind you, we're working on figuring out an expectation value, okay, an expectation value about how far apart are particles. So what do we calculate? Well, we want to know the difference between their positions. So the difference between the position of particle 1 and particle 2. Okay, so that's this vector. We'll square it to get a distance, okay, or a distance squared. And then take the expectation value of that. Okay, so just by doing algebra to expand that, we get that this is the average of R1 squared plus the average of R2 squared minus 2 times the average of this dot product. Okay, so this is an expectation value, or really here 3 expectation values, which we can calculate in any wave function, right? For a combined 2-particle wave function for particle 1 and particle 2. We did that first for the case of distinguishable particles, where we would say particle 1 is in state A and particle 2 is in state B, so that the wave function is this product of psi A for particle 1 and psi B for particle 2. So the wave function is this product, and so then we can calculate any of these expectation values in this combined state, okay? And we did that. We got out the average of R1 squared. It's the average of R squared associated with state A, because particle 1 is in state A. And likewise, the average of R2 squared is the average of R squared associated with state B, because particle 2 is in state B. And then the average of the dot product is the dot product of the averages. It's the dot product of an average R associated with state A and an average R associated with state B. Okay. This is the result for distinguishable particles. Okay. But what if the particles are not distinguishable? Okay. What if you have 2 identical bosons or 2 identical fermions? Okay. In that case, the argument was that the wave function needs a certain symmetry or anti-symmetry. If you have bosons, then the wave function has to be symmetric if you swap the labels for 1 and 2. If you have fermions, the wave function needs to be anti-symmetric if you swap the labels for 1 and 2. Okay, so we're doing both cases at once with this wave function psi plus or minus, right? The top sign means for bosons and the bottom sign means for fermions. Okay, so then we get a result for the wave function that looks like this. And this kind of wave function is neutral about which particle is in which state, right? This wave function doesn't care whether particle 1 is in state A or particle 2 is in state B or vice versa. The only difference between bosons and fermions is whether it's a plus or a minus in between those things. Can one little plus or minus sign make a big difference? Let's find out. Okay, that's what we're going to see here. Okay, so here's the calculation that we started yesterday. Okay, so there's a calculation of R1 squared. All right, and this is our usual integral sandwich, right, where we have an integral over all the variables of the wave function complex conjugate times the thing that we're averaging times the wave function. Okay. Now here, the wave function is this combination of terms. The wave function complex conjugate is this combination of terms. Okay, so it's 2 terms times 2 terms. That makes 4 terms we have to figure out. So that's what we did yesterday. Okay, we got this set of 4 terms. Luckily, 2 of them are 0 because our single particle states, A and B, are assumed to be orthogonal to each other. So then the average of R1 squared works out to be this thing. It's different from our case of distinguishable particles because we have a wave function that is neutral about whether particle 1 is in state A or state B. Okay, and so the average of R1 squared is the average of R squared associated with state A and R squared associated with state B. The same thing for particle 2. Okay, that's as far as we got. And so now I'm going to try to do the remaining average that's needed, which is the average of the dot product of R1 dot R2. Let's see how that goes. Okay, so if we want now the average of, well, here, I'll write this an average of R1 dot R2. Okay, this is, as usual, an integral sandwich. So an integral over R1, an integral over R2 of the wave function psi plus or minus star times the thing we're averaging, which is R1 dot R2, times the wave function itself. Okay, and now we need to put in that this wave function is 1 over root 2. Well, you know, the thing I was just writing. Psi A of R1, psi B of R2, plus or minus psi, whatever it is, B of R1, psi A of R2, psi B of R1. Okay, and the same thing for the complex conjugate over here. All right, so psi A star of R1, psi B star of R2, plus or minus psi A star of R2, psi B star of R1. Okay, so once again, we have 4 terms we have to figure out, right? Because it's 2 here times 2 here. Okay, so let's do it. And okay, yeah, let's do it. Okay, so there's an overall factor of 1/2 because of the 1 over root 2 times 1 over root 2. All right, now, let's see. Let's first do the term with the first stuff here times the first stuff here. Okay. And once again, same as yesterday, I'm going to write the R1 dependent stuff out here and the R2 dependent stuff over there. Okay, so we have psi A star of R1, psi B star of R2, okay, and then we have an R1 dot R2, and then psi A of R1, psi B of R2. Okay, that is the first term. Okay, 3 more to go. Okay, so there's a term where we have the first thing here times the second thing there. Okay, so here there's a plus sign. Here there's a plus or minus sign. So the product of those makes plus or minus. And again, I'll do integral over R1, integral over R2. Okay, so it is psi A star of R1, psi B star of R2. Okay, then R1 dot R2. Then psi A of R2, psi B of R1. Okay, half done. Now we need to do the second piece here times the first piece there. Okay, so that is plus or minus sign on this side times plus over there. So plus or minus here. Okay, so integral over R1, integral over R2. We have psi A star of R2, psi B star of R1, then R1 dot R2, then psi A of R1, psi B of R2. Okay, and the last line, we have to do the second times the second, okay? So there's a plus or minus sign times a plus or minus sign. So if they're both plus, it's plus. If they're both minus, it's plus. Either way, it's plus. Okay, so plus integral over R1, integral over R2. Okay, psi A star of R2, psi B star of R1, R1 dot R2, then psi A of R2, psi B of R1. Okay, so here are all the terms. Now we just need to sort of interpret them, figure out what they mean, and figure out if any of them are 0. Okay, so let's think about the first line first. Okay. In the first line, suppose we look at this term. Okay, this is the average of a position, R1, associated with a state A. Okay? It's a position in a state. We could call it the average of R associated with state A. Here, it's the same thing. It's the average of R, but now associated with the state B. So the dot product of those things. Okay. Down in the bottom, this is the average of R associated with state B. This is the average of R associated with state A. Okay. Now, don't be confused by the fact that the integral here is an integral over R1 with the psi A's. And here it's an integral over the R2 with the psi A's. Because within the integral, the variable that you're integrating over, that's like a dummy index. You're just summing over or integrating over whatever this variable might be called, but you could relabel it to be R, or you could relabel it to be anything, right? You could call this variable Fred, integral d Fred of psi A star of Fred times psi A of Fred, right? So you could call it anything. It doesn't matter what you call it. Okay, and it gives you an average of that thing associated with psi A. Okay, so that's the interpretation of half of the terms. Okay, what about the other terms? Well, if we look at this kind of a term, it's not necessarily zero. Right? This is not necessarily zero. This is not necessarily zero, right? These are not just inner products of psi A and psi B, right? Instead, these things have an operator in the middle, right? This is an inner product of a wave function. Right, here's a wave function, operator, wave function. Wave function, operator, wave function. Okay. This is just like saying there's a bra, well, this whole thing is a bra, operator, ket. Okay. Bra, operator, ket. So we could write this with our bra-ket notation. Right? We could write this out as the bra A acting on the operator R, the position operator, and then the ket B. So this is, it has this kind of operator structure, right? Bra, operator, ket. And the same over here. This thing is the bra B, the operator R, and then the the ket A. Right? These things are matrix elements. You remember how we had matrix elements of any operator, right? And so here, I'll just put it over in the margin somewhere. I'll say, recall when we studied the matrix elements of an arbitrary operator Q. So we could say that the matrix elements of Q, the Q sub JK, that was equivalent to the bra J acting on the operator Q, acting on the ket K, right? You remember that stuff from a few weeks ago, right? That is just what we have here, right? These things are matrix elements of the position operator. Okay, it's a matrix element of the position operator. That's what's in the middle, there and there. So this is the position matrix element between state A and state B. And this is the position matrix element between state B and state A. Okay. The same thing is true on the next line. On the next line, we have B, R, A. Okay, the bra B, the position operator, and the ket A. Okay, this thing is just like this thing, right? Except that the variable that you're integrating over has been relabeled as R1 instead of R2. Okay, but it's the same integral. It's the same thing to calculate. And likewise, this is A, R, B. So it's that matrix element, okay, which is the same as what's right over there. And you also remember that because Q is a Hermitian operator, it is equal to the complex conjugate transpose, right? That Q J K is equal to Q K J complex conjugate. Okay, so that's equal to the complex conjugate of K of this combination, right? The bra K acting on Q, acting on the ket J. So that means that whenever you have the product of those things, so K, Q, J times J, Q, K, that's equal to the matrix element times its own complex conjugate. So that's the absolute value squared. So that's what we have over here, because we're multiplying these terms on line 3 and also on line 2. We're multiplying those terms. So we have the complex conjugate times the matrix element. So it's the absolute value squared. Okay, so to compile all of these results, all right, let's do it. So this is that the average of R1 dot R2 is 1/2 of, let's see, in the first line, we have the average of R in state A dotted with the average of R in state B. That's also true on the last line, the average of R in state A dotted with the average of R in state B. So there's 2 of those terms, 2 times the average R in state A dotted the average R in state B. And then we have plus or minus two copies of the matrix element absolute value squared. So plus or minus two copies of the matrix element absolute value squared. Like that. Okay, and so here you can see that the factors of a half and 2 cancel each other. So this is equal to the average R in state A dot the average R in state B plus or minus this matrix element squared. Okay, so this term is just like what we had for the case of distinguishable particles. This term is new. This is a new thing for bosons or fermions that's different from distinguishable particles. So if we go to figure out the thing we're really trying to calculate, the thing that we're really trying to calculate is the average of R1 minus R2 squared. So that is the average of R1 squared plus the average of R2 squared. All right, we figured that out before. So it's this thing plus the average of R2 squared, this thing, okay? Those are identical to each other. All right, so that's the average of R squared in state A plus the average R squared in state B. Okay, then minus 2 times the average of the dot product. So minus 2 times the thing that's just calculated right here. So minus 2 times the average R in state A dotted with the average R in state B minus or plus 2 times this A, R, B matrix element squared. And here, the minus sign, the top sign, is for bosons, and the bottom sign, the plus sign, is for fermions. And by comparison, when we had distinguishable particles, let me copy and paste that result. That's this thing here. For distinguishable particles, copy. Right. Paste. Aha. For distinguishable particles, it's like that. Okay, so when you compare these things, you can see the first 3 terms are just the same, right? This term and this term and this term. Okay, but the difference is this last term. The difference is the last term, which has a negative sign for bosons and a positive sign for fermions. Okay? And the magnitude is given by this matrix element squared. So what is this? What can we say about it? I mean, I don't know what it is in general. It depends on what are the states A and B. But the one thing that we can be pretty sure of is that this absolute value squared, here I'll draw it to include the square. This absolute value squared is positive or 0. Right? It might be 0, but it can't be negative. It can't be complex. Okay, so this is some positive number there. And for the case of bosons, we are subtracting a positive number. For the case of fermions, we are adding a positive number. Okay, so that means that for the case of bosons, this separation squared is reduced compared with distinguishable particles. And for fermions, it's the other way around. For fermions, the separation average is increased, again, compared with distinguishable. Now, I should mention, I haven't talked about spin in this calculation. I've just been writing about wave functions that depend on position, okay? And that's because I've been assuming all along that this is for the same spin state, okay? So I should put that as a proviso here, I guess. These are bosons of the same spin M. And likewise, fermions of the same spin M. Okay, so the point of all this is just to tell you that this distinction between bosons and fermions really matters, right? That it actually affects stuff that we can calculate, and it affects stuff that people can observe, okay? It means that bosons are closer together compared with distinguishable particles. And fermions tend to be farther apart compared with distinguishable particles. Okay, and so when I was a student, one of my professors referred to this kind of thing as the gregarious property of bosons, right? That bosons like to be close to other identical bosons, right? That they tend to be closer together just because of the symmetry requirement associated with the wave function. And so that's sort of gregarious, and fermions are the opposite of that, right? So fermions are nerds, right? Fermions tend to stay farther apart from other identical fermions, okay? And so it's like the opposite of gregarious. This is actually a calculatable and observable experimentally property associated with bosons and fermions. Okay, now I know this was kind of a long calculation. Some people kind of lose their patience with long calculations. It occurred to me I could try to show you the same information in a more visual way. Okay, so let me switch over to Mathematica. I just had this idea yesterday about how to make a visualization of this. So let's see if this is interesting for you. All right, so I'm going to stop the iPad, and I will start sharing Mathematica. Okay, you see that guys now, right? Okay. Let's do the example of two particles in a one-dimensional box. Okay, because the one-dimensional box was the first thing we did this semester. It's like the simplest example that we can always come back to. Okay, so suppose we have two particles in a one-dimensional box. Okay, now you already know what are the states for a single particle in a one-dimensional box. Okay, you know that the first state is this thing, right? It's this sine of pi x. And I'm letting the box size be 1 in some system of units. Okay, so the A parameter is 1. Okay. So that is a wave function like this. Okay, and it's associated with a probability density, which is the wave function squared. It looks like that. Okay, right? That's familiar to you from the beginning of the semester. Right? And you know that the second state for a particle in a one-dimensional box is sine of 2 pi x. Right? So it looks like this for the wave function, right, with a single node in the middle. And the corresponding probability is the wave function squared. Okay, so it has two peaks in the probability. Okay, so let's think about the situation where one particle is in the first state and one particle is in the second state. Okay, and compare it for distinguishable particles versus bosons versus fermions. So for distinguishable particles, we would say that the wave function is like this. Okay, so it's the wave function for the first state associated with the first particle, and the wave function for the second state associated with the second particle. Okay, so it gives us this nice function of two variables, x1 and x2. Okay, so it's the sine of pi x1 times the sine of 2 pi x2. Okay, that's what it means to say that the first particle is in state 1 and the second particle is in state 2. Okay. So we could make a nice three-dimensional plot of this wave function, which looks like this. Okay, so this is a plot as a function of x1 and x2. Okay, x1 is on this axis, x2 is on this axis. And so here's the shape of the wave function as a three-dimensional plot. Okay, and the probability is the square of the wave function. So it is this thing. Okay, so you can see that the probability has two peaks, right? It has a peak over here where particle 1 is in the middle and particle 2 is around x2 equals 1/4. So particle 2 is on the left side. Okay? And there's another peak over here where particle 1 is in the middle and particle 2 is on the right side. Okay. So does that sort of make sense to you guys? Maybe? Okay. And we can check that this state is normalized. All right. And so, yes, it is. That is, if we take the probability and we integrate it over all x1 and all x2, you get 1. It's our usual normalization. Okay? And what if we want to know how far apart are the particles? Well, we can take the average of x1 minus x2 squared. It's a perfectly reasonable thing to average. Okay, that's just like all the big calculation I was just doing. So if we take that quantity times the probability and integrate it over all x1 and x2, we get a number, 0.1. Okay, so it's a specific prediction for how far apart are the particles in this state. Right? Now, let's repeat that calculation for bosons with the same spin. Okay? So, in that case, we have a wave function for bosons, which is just like I was constructing on the whiteboard a few minutes ago. Okay, so it's psi A of x1 times psi B of x2 plus the other way around, psi A of x2 times psi B of x1. Okay, and then divided by root 2 so that it'll be normalized. Okay. Let's make a plot of that. Okay, here is the plot of that function in terms of x1 and x2. Okay. And then the probability is that wave function squared. So it looks like this. Okay. You can see just with your eyes, this is different from the case before, right? Now, the peaks are in different places. Okay, there are still two peaks, but the peaks are over here and over here. Okay, so there's one peak where particle 1 is on the left and particle 2 is also on the left. And there's another peak over here where particle 1 is on the right and particle 2 is also on the right. Okay, so that's a visualization of the gregarious property, right? That's one particle says to the other, "Oh, you want to be on the left? I want to be on the left too. You want to be on the right? I want to be on the right too." Okay, here's how they are associated with each other. They tend to be in the same place. Okay, now not always. There's some probability for them to be in different places, but they tend on average to be in the same place. Okay, so we can check the normalization of this state, okay, by integrating the wave function squared over all x1 and x2, and it comes out to be 1. Okay, and then we can find the average separation squared. Okay, so that is, we can take x1 minus x2 squared times the wave function integrated over x1 and x2. And this is a number. It's a smaller number than we had before. Okay. It's actually a lot smaller, right? Before it was about 0.1, now it's about 0.04. Okay, so this is saying that the particles, are really closer to each other just because of this symmetry. Right? Perhaps you could visualize that by looking from above, right? Here, if we look from above, right, the line of x1 equals x2, that's the 45-degree line, right? This is x1 equals x2. Okay? So the average of x1 minus x2 squared, that's saying how far are you away from the 45-degree line, okay? And so here, the particles tend to be pretty close to the 45-degree line, compared with the distinguishable particles, where it's sort of farther from the 45-degree line. Right? Here's the 45-degree line there. And there's a lot of probability to be in other places besides that. Okay. How about for fermions now? Okay. For fermions, again with the same spin, all right? The wave function looks just like for bosons, but with a negative sign in the middle instead of a positive sign, okay? So you say, how much difference could that make, negative versus positive? Well, it makes a lot of difference, okay? So here's a plot of the wave function now for the fermions in terms of x1 and x2. And then the probability is the absolute value squared of the wave function. Okay. It still has two peaks, but the peaks are in different positions, okay? Now, there's one peak where particle 1 is on the right side and particle 2 is on the left side. And there's another peak where particle 1 is on the left side and particle 2 is on the right side, okay? So it's like the particles say, oh, you're on the right? Okay, I'll be on the left. Oh, you want to be on the left? No problem, I'll just go over here on the right, right? Which sounds like something I would say, okay? And so, you know, this is the nerd-like property of fermions, right? That they tend to be farther apart, okay? And so here, if we look at it from above and we see, whoops, sorry, I'm not navigating this very well. Okay, I'm not a pilot. Okay, so if we try to make this be, what am I doing? Here it goes. No, here it goes. All right, here's x1, here's x2. All right, here's the 45-degree line. All right, there's no probability of being exactly on the 45-degree line, right? That's 0. And then most of the probability is around here or around there. It's far from the 45-degree line. Okay? And so if we calculate the normalization, still normalized. If we calculate the average separation, now it's bigger, right? This average separation now is 0.168, right? So it's bigger than the average separation associated with distinguishable, and it's much bigger than the average separation associated with bosons, okay? So that's, you know, a real physical consequence that just comes from the symmetry of the wave function. Okay, here, this is the first time I made this kind of visualization, but maybe this is actually easier to look at than the whole big calculation, and it doesn't take an hour like the whole big calculation does. So I should remember this. Okay. All right, just for comparison, here's a little practice visualization thing. What if we had one particle in state number 1 and one particle in state number 3? Okay, so we do states 1 and 3 instead of 1 and 2. So I'll just change this to a 3. Okay. Here's state number 3, right? You remember this thing from when we studied the particle in a box. Okay. Here is the corresponding probability. Okay. All right, let's repeat all of our calculations here. All right, for distinguishable particles, now here's what the probability distribution looks like. Okay, so particle 1 tends to be right in the middle. Particle 2 could be on the left or in the middle or on the right. Okay, 3 peaks. How about for bosons? Okay, well, now, here, I'll go back to the default angle here. You can see that the main peak is where particles 1 and 2 are both in the middle. Okay? so they're close to each other. Okay. There are also subsidiary peaks. Okay. There's a peak here where both particles are on the left. Here, where both particles are on the right. Okay. Now, there are also peaks there and there where they're on opposite sides. So, those things can happen too. They don't have to be in the same place. It's just a matter of probabilities. All right. And now what about for fermions? So for fermions, here's our probability distribution in terms of x1 and x2. Okay. So there are peaks where x1 is in the middle and x2 is on the left, or x1 is in the middle and x2 is on the right, or vice versa. Particle 1 is on the left or the right, and particle 2 is in the middle. Okay? But there's no probability on the 45-degree line that is 0. So yeah, so hopefully this gives you some kind of visual impression of how the probabilities change, and they actually change a lot, right? Just based on the symmetry of the wave function. Let me say just a couple of brief things about this also. In general, let me go back to the iPad now. Turn the iPad back on. Okay. Share iPad. Go. Okay. Let me emphasize one more point. This whole thing is for non-interacting particles. That means that the potential energy is a potential energy as a function of R1 and R2. That's a potential energy as a function of R1 plus a potential energy as a function of R2. Okay, that means that there is no interaction potential energy. You remember, this is the simple case, right, where we could calculate some things exactly, right, as opposed to the complicated case where the potential energy looks like a V of R1 minus R2, right? That would be a complicated thing where we probably can't calculate anything exactly. Okay, so all of this stuff happens without an interaction potential energy, okay? This is what people refer to as non-interacting particles, okay? Now, I remember when I was a graduate student as a TA, there was one time when I got into an argument with a student in the class, and the student was saying, what do you mean this is non-interacting particles? These particles are clearly interacting with each other, right? I mean, if one particle tends to be on the right and one particle, other particle goes to the left, that's an interaction, isn't it? Well, this is a question of nomenclature, right? It's a question of terminology. I can see the student's point, right? Logically speaking, the particles are aware of each other. They're doing something in response to each other. As a matter of terminology, people use the word non-interacting particles to describe this, to say there's a situation where there's no interaction potential energy. And so there's no interaction force that comes from the potential energy. But still, the particles do have some effect on each other. Okay, and so, what do we call that? So we could say, how will I express that as a sentence? Even, even without the interaction potential energy, identical bosons or fermions still affect each other. Okay, and the word that people use for this effect is called exchange. Okay, and it's called exchange because it comes from the symmetry under exchanging the labels, right? That because we have this symmetry or anti-symmetry under exchanging which thing we call particle 1 and which thing we call particle 2, right? That seems like it should just be a matter of labeling, but now we see that it actually has real physical consequences, okay? And so people refer to this thing sometimes as the exchange interaction or the exchange force. Okay. And so this thing is not a potential energy, but it still has physical effects, right? It's just a matter of the symmetry, but it has physical effects anyway, okay? And in the textbook, they call this a geometrical effect. That's a funny word. I've been thinking for a little bit about what do they mean by geometrical? Where's the geometry? I think what they are describing is something in the geometry of Hilbert space. So not in the regular geometry of the one-dimensional box, for the example that I gave you, but in the geometry of Hilbert space, about what states are allowed in Hilbert space. And when you have fermions, there is more space in Hilbert space for states where the particles are far apart. And there just isn't so much room in Hilbert space for situations where the particles are close together. And vice versa for bosons. For bosons, there's just more room in Hilbert space for possibilities, for situations where the particles are close together, and less room for situations where the particles are far apart. And so that makes a geometrical effect, which tends to keep bosons closer together and fermions farther apart. And one other point that the textbook makes is that this exchange interaction it depends on the matrix element that we calculated, right? So it depends on this matrix element of the position operator between the single particle states A and B, okay? Now, this matrix element is large if the states psi A and psi B overlap a lot. That is, if there are regions as a function of x, say, where psi A is like this and psi B is like that, so that there's a big overlap region where they both are large. Okay, so if you have two electrons that are close to each other, there's a big overlap region, right? And it works as long as the centers are not too far apart. Okay. By comparison, right, if you have a situation, say, where there's an electron in Kent and an electron in California, right? So let's say here is an electron in Kent. And over here is an electron in California. Okay, the overlap is hardly any, right? That there's hardly any region where these wave functions are both substantial, right? That the California one gets extremely small before the Kent one gets big, okay? And so in that situation, the matrix element is small. And so for that reason, the exchange interaction is small, okay? And so you don't really care whether you have a symmetric or an anti-symmetric state between an electron in California and an electron in Kent, right? Because of the lack of overlap region, the physical consequence is small, right? But when the electrons are right up close to each other, that's where it's a big physical effect. Okay, so here, you know, the overlap matters a lot. The symmetry of the wave function matters a lot. Okay, I think that's what I wanted to say about section 5.1. Okay, so that is the introduction to the concepts of bosons and fermions. Okay, and on Thursday, I'm going to apply this to what happens in atomic physics and maybe a little bit about magnetism also. So consequences of this for atomic physics and magnetism. But before that, right, so for a few minutes today, I want to talk about the final exam. Okay, so for the final exam, I need to give you a final exam in a couple of weeks. And I have hosted a couple of practice exams on the Google Drive. Okay, and so I just put those up this morning. So practice final exams are posted now. These are exams from the last 2 years when I taught this course. And so in 2019, that was a regular final exam in the regular final exam time. And last year, it was a take-home exam because of the pandemic. for this year, we're still in the remote instruction format, and so I want to do a take-home exam again. I would like to do it in this 24-hour take-home format again. Unless any of you object to that, because to me this seems. I can't stand the business of proctorio and looking at students for 2 hours while they're doing their work. And so I would rather just give you 24 hours to do it, and it'll be more than enough time for whatever you know how to do on this test. Okay, so I'll make it the same format as the midterm. All right, same format as the midterm. Maybe an extra, a little bit longer than the midterm, because it's a final instead of a midterm, but the same general format. So once again, open book, open notes, open using integration software, that sort of stuff. But just not allowed to communicate with any other live humans, okay, during the test. Now, the official time for the final exam is, let me look that up on my iPhone. I had that here. That was Friday, May 7th. I believe it's the Friday in exam week. Friday, May 7th at 10:15 to 12:30. Okay. Personally, I don't really care when I give it to you. I can pick a 24-hour period. I was inclined to maybe pick a 24-hour period that includes that Friday, because then I'll be able to tell people I was doing my best to be close to the official time. So I could make it go from Friday to Saturday or Thursday to Friday, something like that. Okay. But I can put it up to you. If any of you guys want to express an opinion, please speak up. Okay, so let me, you can express your opinion out loud, or I'll even turn on my chat and you can express your opinion in the chat. Either way. Does anybody want to express an opinion about when you want the final exam to be or not to be? I cannot hear. Chris?
2 mute buttons. Can you hear me now?
Yes.
I'm voting Thursday to Friday, but if that's not good for everybody else, just let me know. I'm good with the team.
Okay.
I would prefer Thursday to Friday as well.
Okay.
Same.
Okay. Brian is putting on the chat. Okay, Thursday to Friday. All right. Is there anybody opposed to Thursday to Friday? Okay, speak up or type up if you are opposed. No, I am not hearing anything. Okay, so let's say Thursday to Friday. Do you want to say what, noon to noon, 2 p.m. to 2 p.m.? What do you guys feel like? Doesn't really matter to me.
Noon to noon works fine for me. Nobody else.
Sure. Well, doesn't matter to me. Okay. Everyone's all right with that? Okay. So here, I'll put that up on the iPad and I'll write it down so everyone can see. Okay. So our decision is Thursday to Friday. So that's May 6 to 7, 12 noon to 12 noon. Okay, you're all set with that? Great. Fine with me. Good, good. So you can take a look at the practice tests on the Google Drive, and of course, ask me questions about those things anytime. All right, I will stop here. I'll let you out a few minutes early to compensate for all the days when I go overtime. And I will see you guys on Thursday for some applications of fermions. All right, so long.